So in this exercise, we're asked to kind of be creative here and do a little bit of design work. And what they're asking us for in this equation, or the setup, is they're giving us two voltage sources, which is V1 and V2. And they're saying they want us to design a resistor network such that the output voltage, V0, will be a combination of the V1 and V2 that are related in this way. Now, in addition to this, they're also asking us to use the minimum number of resistors, and we're also to assume that there'll be no load on the network. So these are some pretty specific criteria. So again, two voltage sources, minimum resistors, no load on the output voltage. So the first pass we want to think about how to do that. There may be multiple ways to do it, but this seems to be the most simple approach. And again, we have our two voltage sources. We're going to allow one resistor per voltage source, so that should be the minimum number of resistors. This is our output voltage, and again, no load across there, so it's going to be an open circuit. So this being the case, see if we can come up with a way to solve this problem, or to design this circuit that they're asking for. So the first thing we want to note or look at is this node A. And we see that node A, the voltage at that node is our output voltage V0. So that's something that's useful to us. The next thing we want to notice is if we consider a nodal analysis, there should be, and we consider leaving the node as positive, we should have one current here. We'll call it I1. Write that a little neater. I1. And then we should have another current leaving the node going this way, which we'll call I2. So one way we could construct equations is do a nodal analysis of node A and come up with those equations. So let's do that. So like we said, starting at node A, like we said, if we sum up the currents going through node A, it should just be I1 plus I2, and that should equal to 0. That's Kirchhoff's law. Well, now we can use Ohm's law and recall that, I is equal to the voltage over the resistance. So that being the case, we need to determine how to replace I1 and I2 with the Ohm's law representation. So looking at the first side, I1, we see that we said that this right here at node A was V0, right? So if we go from V0 to V1, that would be our voltage difference, or our voltage in that circuit. So we can write that as V0 minus V1, and then our resistance is just going to be R1. So it's divided by R1. So there's our representation for I1 using Ohm's law. Now we need to do the same thing to the other side. So here, same thing. This is V0, we've said already. So the voltage difference around this circuit is the difference in V0 and V2. So that'll be V0 minus V2. And again, the resistance in this case will just be this R2 value here, R2. And we should be able to set that equal to 0. Okay, so now we have our equation. We have the resistances, we have our output voltage, and we have our two source voltages. And those are the only components in the equation. So we should be able to work with this. So the first thing we want to do is multiply everything through by R1 and R2. So again, we'll just multiply everything by R1 and R2. So when we do that, the I1 term goes to V0 minus V1, and that's going to be times R2. And then the second term, if we multiply through, that's going to be V naught minus V2, and the R2s will cancel out, so then you'll be left with an R1, and anything times 0 is 0, so the right-hand side remains 0. So now we want to multiply everything out, and so when we do that, we get V0 R2 minus V1 R2, and then the second term is going to be V0 R1 minus V2 R1. That's going to equal to 0. All right, so now we're trying to solve for the output voltage. So that being the case, we want to put the V0 terms on the left-hand side of the equation, and then the non-V0 terms on the right-hand side of the equation. So we'll just add those since they're negative. And when we do that, we'll come up with V0 R2 plus V0 R1, and that's going to be equal to V1 R2 plus V2 R1. And we should be able to see that this is the same thing if we take out a V0. It's just R1 plus R2. So now if we divide both sides by R1 plus R2, what we would have then is V0 is equal to R2 over R1 plus R2 times V1, and then plus R1 over R1 plus R2 V2. So now we should be able to recognize that this equation right here is in the same format as this equation here. So that being the case, we need to set the V1 argument equal to 2/5 and the V2 argument to 1/5. So we can come over here and do that. So then that's going to say R2 over R1 plus R2 is going to be equal to 2/5. And then R1 over R1 plus R2 is going to be equal to 1/5. Okay, so if we cross multiply these, then what we'd have is 2 R1 plus R2 is equal to 5 R2. And then the second equation would become R1 plus R2 is equal to 5 R1. And these are just two equations, two unknowns. So if we solve these out using just our simple linear algebra, what we will come up with then is, I'll put this over here, is that our R1 is going to be equal to 5 over 3 ohms, and that our R2 is going to equal to 10 over 3 ohms. So this is the solution to the problem. If we have two voltage sources and we want the output voltage using this circuit here to give us a relationship of 2/5 of the first source plus 1/5 of the second source, then we need two resistances, R1 equal to this value and R2 equal to that value, and we connect them up, and that's what we should get at the output voltage.